as I was saying, this portion of the video is going to be dedicated to the answers and why they are the answers of the first 2 pages or so, these 2 pages of the physics review test that was given in class. Now, this doesn't really require too much writing, but let's take a look at the first one. And this is the true or false section. Question 1. The normal force, Fn, that acts on an object is always equal in magnitude and opposite in direction to the gravitational force, Fg, that is acting on it. So, that's a good question. That's actually a very good question, primarily because of the way it's worded. Now, what we're interested in, what kind of caught my attention to this, is the equal in magnitude and the opposite in direction part. That's kind of what caught my attention in that question, because the answer is no, they're not always equal, which means that'll be false. And the reason that's false is because it's saying that the Fn is always opposite in direction to the gravitational force. Well, it's not entirely true. We've seen exceptions to this, especially when we were doing when we were introduced to drawing FBDs at the start of the unit. If you remember, yes, it would be true in this type of scenario. Now, it would be true in this type of scenario where the object is not falling through the earth or the ground, and it's not flying upwards. Now, it would be true in that case. That would be totally true. The Fn is totally opposite of the Fg. But in this scenario, that's not very true, because this isn't the only type of FBD you can have. You can have an FBD that looks like this, for example. You can have an FBD that looks like this, on a slant. That's going this way. And yes, the Fg is still acting downwards, but the Fn is not acting like this. By law, the Fn always acts parallel to the surface. Or not parallel, what am I saying? Perpendicular. It always acts perpendicular to the surface. So in this scenario, the Fn would be acting like this. And just from that little diagram alone, we can confidently say that number 1 is false. Because, just to recap, the Fn is always perpendicular to the surface. It's not always going to be directly opposite of it. So that's the reason why that is like that. Moving on, let's quickly erase this. So, number 2. The same net force acts on 2 objects having different masses. The more massive object will experience the greater acceleration. So, let's think about this one, because the wording could be tricky. So this is saying that the more massive object will have. The more massive object will have the greater acceleration. So that's not true whatsoever. And there's a really simple way of thinking about this. If you were to shoot a cannonball out of a cannon, it's going to go a lot. How can I word this correctly? Okay, I'll think like this. If you were to throw a squirrel, if you were just throw a squirrel into the air as far as you could, the squirrel will experience a much greater acceleration because of the fact that it's lighter. The reason for that is because of the fact that there isn't as much opposition to it. And that's taking into account, air friction, wind, anything like that. But generally speaking, always speaking for the most part, and if not always, usually, the smaller object will always travel at a higher acceleration. Try thinking about this. If you tried throwing a hippopotamus and a squirrel, the squirrel is going to have a much higher acceleration if you can even throw the hippo. So I don't think that one needs any writing. Number 3. For two given surfaces, the coefficient of static friction is generally greater than the coefficient of kinetic friction. So, if you remember what those terms are, the coefficient of static friction is the ms. All right, static friction coefficient. And mu k is kinetic. Now, just from analyzing this, just to recap, static means stationary, so you're not moving, and kinetic means moving, which is where the first unit, the kinematics, is drawn up because they are equations, for example, that deal with motion, the motion of objects. Now, this isn't really more so. You could do calculations for this, but strictly speaking, on a test where you expect to just kind of remember this, yes, static friction will generally be greater than the force of kinetic friction. If you guys remember, we had the graph in class that went like this. And also from labs, you may have seen if the lab was done correctly, which we don't know because he hasn't given them back yet. The mu k will often go up here. Mu s, static friction will often go up here until it reaches some certain point where it will just drop and mu s will begin. Mu k, I'm really maxing these up. So mu s, mu k. So the reason that mu s is so much higher than mu k usually is because objects resist when you push them. For example, let me see if I can do this. My calculator have it. I'm going to slowly start applying force, and right there, it just moved a bit. You probably didn't see it, but when you apply force on something and you feel that jolt, that is the static friction breaking, and then you're able to move at a speed with a less amount of force. But generally speaking, the mu of s is bigger than the mu of k. And that's just a rule. Now, with regards to number 4, free body diagrams include only the... and for the last question, for coefficient of static friction, it's true. It's true. For number 3, it's true. Just to recap, number 1 is false, number 2 is false, and number 3 is true. Number 4, free body diagrams include only the forces responsible for an object's motion. Now, I was talking with a few people, and it was more so 3/4 of people gave the right answer, the other 1/4 gave the wrong answer. They weren't really thinking very clearly. Now, let's just recap on what an FBD is. An FBD stands for free body diagram, right? So, sorry, I'll move over to this side. An FBD is an FBD. Oh, horrible. Still trying to get used to writing on this thing. So, we have a free body diagram. Now, just to think of what that actually means, a free body diagram shows what is happening to an object. Now, if we have an FBD, if we have, for example, myself right now, according to this question, a free body diagram includes only the force responsible for an object's movement. So, looking at myself right now, my feet are stationary, I'm stationary, I'm moving my arms, But in terms of my whole body, I am not moving forward, I'm not moving backward. So according to that statement, I would not be moving, and that is my FBD. That would be my FBD if that question was true, because there's nothing responsible for movement. I'm not moving. So that would be my FBD. But no, that's not a real FBD. My FBD, whether we know it or not, would look like this. The reason being is that while I may not be moving, there are two forces acting on me, one going up, one going down. Fn going up and Fg going down. So the key in this question is free body diagrams include only the forces responsible for an object's motion. No. Free body diagrams include all of the forces acting on an object. So that is false. Oh, let's move on. That question was, that would be for the most part, a free mark. Most of these are actually quite easy. So, look at the next question. We have number 5. An object has two forces acting on it, 8.4 newtons going south and 7.5 newtons going east. The magnitude of the net force is... Alright, so... Good question. So, this is, I believe, the only question in this section that actually has you doing any sort of work. Okay, so, I'm trying to remember the formula right now. Oh, is it minus? I'm going to go with minus. Okay, so, we have two forces going on right now. We have the Fn, or not really Fn, we have one force going like this, which is 8.4 newtons. And then we have another force like this, which is 7.5 newtons east. 7.5 newtons. So, when you draw like this, it's pretty self-explanatory what you have to do. Just draw a line. What is this side? And that's what I was wondering about the formula. I can't remember what the formula is. But when you have a question like this, what you do is you take both sides. So we're going to make this. We're going to make this this A and this B. Now, what this boils down to is a simple Pythagoras thing, equation triangle. So the equation is as such: c squared equals a squared minus b squared. I figured it can't be plus because the number would be too big for what options we have on the page. So we can just go ahead and plug everything in. Okay, this is not good. I can't remember. Is it plus or minus? All right, let's go with plus. I don't know if it is this, so I'm sorry if it is. If it isn't, but let's act like it is. So 8.4 squared plus 7.5 squared. What the hell is this? Oh, B. So using that, we can just calculate what those would equal, and find out what they are. 8.4 squared, no, not 804 squared, 8.4 squared is 70.56. 70.56. And then we just have to add 7.5 squared, which is 56.25. This is 6. Sorry about that. 56.25. And adding these together, 70.56 is 126.81. Now, don't forget we still have our c squared here, which means we have to square it, or square root it, I should say, to give us c equals, the square root of the answer is 11.26. And looking at our answer is, let's see, we'll round it. 11.2 would be 11.3, but it would just be 11. Allowing the option and the answer to be number C, 11 newtons. So, how we did that? How we figured that out. There was an F net going to the south, so we drew a vertical axis force. We also drew a horizontal axis force for the one going east. We just found the missing side. Now, if I remember, the rest of the questions are quite self-explanatory, but let's take a look at them. So, number 6. An object is pushed horizontally at a constant velocity. What can correctly be said about the forces acting on the object? So, obviously, you may be able to see the answer right now, but it's important just to read all the options. The force or forces acting forward is or are greater than the forces acting backwards. So, that's incorrect, because if it is moving at a constant velocity, the forces should not be greater than each other or less than each other. That would result in an acceleration or deceleration. Number B, let's see. The sum of all forces has a value direction forward. I don't even know what that means, to be honest. I guess it means it's moving forward. I don't know. But let's assume that's wrong. The sum of all forces is 0. That's C. Could that be true? Okay. Well, let's hang on to that one. D. The forces acting on the object can be said to be unbalanced. That's kind of like A. They have to be balanced to be moving at a constant velocity, or else there would be an acceleration or deceleration. And E. Newton's second law best summarizes the effect of the forces acting on the object. Newton's second law is F net equals ma. Yes, yes, that does summarize, how a force is brought, but it doesn't really talk about how it is moving per se. If an object is keeping and maintaining a constant velocity, that means that all forces are balanced on it, and that would result that it is C. The sum of all forces is 0. And the reason it's 0 and not anything else is because if, for example, we have Fg and Fn, Fg and Fn, if we have if Fg is 5 and Fn is 4, 4 minus 5 is negative 1, or it can go 5 minus 4 is 1. Either way, there's an imbalance. Either way, there's an imbalance, so it doesn't work, because it would probably be crashing to the floor. But if it is 0, or let's make this 5. If it's 5, that would mean that 5 minus 5 is 0. Everything is balanced. It's not doing anything it shouldn't be. So that is the answer for that. I repeat, number 6 is C. Moving on to 7. And this one's extremely easy. Which of the following units is equivalent to a Newton? And this is just pure memorization in reality. But you could probably find the answer to that throughout the test, throughout the review package. But okay, let's look at the options. A, kilogram times meter per second. Well, let's go look at it. We know that newtons have kilograms in it. We know that there's a mass, but is it over s or s squared? That's what you have to remember. So it's not that one because of the fact that it's only over s. Number B, grams right away. Newtons are not in grams. That's automatically wrong. C, kilograms per second squared meters. Well, it's got all the right things in it, but they're not actually in the right order. And I'll explain why. S squared over m can be translated to 4, let's go, divided by 2. Let's make it easy. 4 divided by 2 is 2. Easy enough. But if we switch those around, 2 over 4, 2 divided by 2, that's 0.5. Huge difference. So no, that can't be it. What about D though? Kilograms per meters squared? Per second squared? Well, that sounds a little bit more right, but let's make sure we look at all the options. Kilograms times centimeter? No. There is no centimeter, so that's automatically wrong. Which means that the correct answer is D. Finally, number 8. The free body diagram of a wagon being pulled along a horizontal surface is best represented by... Okay, so I think we can draw these out to make it a bit easier to analyze them. So, number 8. And there we have one going out. One moment, I just draw these out. And now we have F. So that's one of the FBDs on the page. Then we have another one. I'm going to make them a bit smaller. I'm going to guess it's FAP, K, and FK. So I can move on to this side. We have another one that they've drawn out for us. Obviously it doesn't look exactly like that, but it's going to have to do. FGA. Sorry about that, that's an arrow, by the way, my bad. Then we have our next one, which is... I'm going to make this one even smaller. Okay, so, oh, we have one more. Good old, why not have one more? I'm sorry about how small these are getting, guys. Should have divided up the page a bit better. FA and FK. So it's a little crammed on this side, but that's not a problem. So the free body diagram of a wagon being pulled along a horizontal surface is best represented by. So let's take a look at that. So the statement does not say that there is not a force of friction. Ergo, we have to assume there is a force of friction. So right off the bat, we can just get rid of 2 of them. We can get rid of this one and the oh gosh, I like how you serious. Now, the free body diagram of a wagon being pulled. Okay, so we now have an option between these 3. Really obvious. As we said in what? I guess it was question 4 on the previous page. about the whole what is shown on FBD. This one doesn't show any force of gravity or force of Fn, so we can go ahead and kick that one out too. Again, with this one, it doesn't show Fn either, so you can kick that one out too. The correct answer is whatever that one is. That would be D. And the reason being is that we have an Fn going up, Fg going down,